everyone, today we'll be looking at complex numbers. So complex numbers are made up of both a real and an imaginary part. By real part we mean just a real number, so these are the numbers you're probably familiar with. Numbers like 0, 1, 2, 3, 4, 5, all of the natural numbers, decimal numbers, integers, irrational numbers like pi. These all form the real numbers that you're used to. But a complex number is made up of both a real part and an imaginary part. An imaginary number, we'll take a look at what that is, but it is real. The imaginary number is real. It's been given the term imaginary, but it does exist in the sense that it has many applications. But imaginary is just what we've called it, but it does exist. So let's take a look at what an imaginary number actually is. So if we have something like a quadratic equation usually has this form. So it's some coefficient multiplied by x squared plus something times x plus another constant. These coefficients b and c may be 0, but the important thing is in a quadratic the highest degree or the highest power of the variable is 2. That's what makes it a quadratic. And usually we can, or sometimes we can factorize this to find the roots of the quadratic. So roots are values of x for which this equation is actually 0. So we can factorize it sometimes to find the roots, but in cases where we can't do that, we use the quadratic formula, which you may have seen before. It looks like this. And this part underneath the square root is known as the discriminant. And when the discriminant is positive, we say that there are, so when b squared minus 4ac is positive or greater than 0, there are 2 real roots to the quadratic. When it's equal to 0, there are 2 equal real roots. So in the first case, when it was greater than 0, there are 2 distinct real roots, so 2 different roots. Whereas when it's equal to 0, there are 2 repeated real roots. But when it's less than 0, well, how can you square root a negative number? There aren't any real numbers such that when you square them, you get a negative. Any real number that you square will give you a positive number. If I square minus 5, I'm going to get 25. So whatever you square, if it's a real number, you'll end up with a positive value. So we can't get a negative under the square root. There's no real solution to this equation. But we can find a solution to this equation if we extend our number system to include the square root of negative 1, which is what we called I. I guess, represents imaginary. So we define the square root of minus 1 to be equal to I. Now, this solves a lot of problems for us because now, say we've got something like negative 36 under this square root. So let's say the discriminant is minus 36. We can rewrite this as square root of 36 times minus 1, which I can rewrite as square root of 36 times square root of minus 1, and we have just defined this square root of minus 1 to be equal to I. So I'm going to replace I for square root of minus 1, and square root of 36 is 6. Back to complex numbers, which are made up of a real and imaginary part. So we usually write them in the form a plus bi. A and b are both real numbers, so this forms the real part of the complex number, and this forms the imaginary part. It's some amount of I, so it's some real number times I, in the same way we had 6i over here. You can add complex numbers by adding or subtracting their real parts. So say we are trying to add this complex number to this one. We will add the real parts, so 2 and 7 are the real parts. Adding them, I get 9, and adding the imaginary parts, which are 5i and 3i, I get 8i. And the same goes for subtracting them. You can take away the real parts and then take away the imaginary parts. To multiply a complex number by another one, you can follow a similar method to how you expand brackets. So if I'm multiplying 1 plus 4i times 5 plus I, we can just multiply the first term in the first bracket by the first term in the second, and then by the second term in the second, and then add that to the multiple of these two as these two. So let's just work through that. So if I do 1 times 5 plus 1 times I plus 4i times 5 plus 4i times I. And simplifying this, 1 times 5 is just 5, 1 times I is I, 4i times 5 gives me 20i. Now 4i times I. Let's look at what I times I is. If you remember, I is the square root of minus 1. If I multiply this by itself, which is kind of like squaring it, well, square root of minus 1 and then squaring that number, that's kind of like doing a function and then undoing it. So we end up with just minus 1. So what we have is plus 4 times minus 1. So I have 5 plus 21i minus 4. 5 minus 4 gives me 1 plus 21i. Let's work through an example of finding the roots of an equation, a quadratic equation, which doesn't have any real roots, it has complex roots. So I'm going to write down this quadratic. If we use the quadratic formula, which, if you remember, is this. So substituting in values for a, b, and c. A is 1, since the coefficient of z squared is 1. B is 6, and c is 25. So we have negative 6 plus or minus 6 squared, which is 36, minus 4 times 1 times c. All of that over 2 times a, which is just 1. So I'm going to simplify this bit. We have 36 minus 4 times 25. So that is like 36 minus 100, which is square root of negative 64. So we can see that our discriminant is negative. Now let's work out what the square root of minus 64 is. So we can rewrite this as square root 64 times square root of minus 1, which gives me 8i. So substituting that in, I end up with this, which if I simplify, dividing the numerator by 2, I'll end up with minus 3 plus or minus 4i. So we've got two solutions for z. Minus 3 plus 4i and minus 3 minus 4i. Now let's look at a concept known as complex conjugation. So, for any complex number, which we write in this form, the complex conjugate, so the conjugate is defined as a minus bi. So we usually use z with a little superscript of a star to denote the complex conjugate, and together z and z star are known as a complex conjugate pair. So let's say we have a complex number, 2 minus 7i. The conjugate pair would be 2 plus 7i. So we've just changed the sign in the complex conjugate. So for any complex number, the product of z and z star will always give a real number. We can see this if we multiply z with z star. This kind of looks like a plus b multiplied by a minus b, which gives us a squared minus ab plus ab minus b squared, which is a squared minus b squared. So let's apply that here. If we multiply these together, we'll have a squared, so 2 squared, minus b squared, which is 7i squared. Let me move this out of the brackets. So we have 4 minus, now if you remember, I squared is minus 1, because I is square root of minus 1, and if we multiply it by itself, then we'll just end up with minus 1. So 7i squared, 7 squared is 49, and I squared is minus 1. So what we end up is 4 minus negative 49, so we end up with 4 plus 49, which is 53. So it's a real number. So when you want to divide two complex numbers, say we want to divide 5 plus 4i by 2 minus 3i, then what we can do is multiply it by the complex conjugate of the denominator, top and bottom. So the complex conjugate of the denominator is 2 plus 3i. So I'm going to multiply it by this. It's kind of similar to how we rationalize the denominator when it has a third at the bottom of it. We multiply it by that same third, top and bottom, which is kind of like multiplying it by 1 because this ratio is equal to 1. So the number remains the same if we multiply this by the same number top and bottom. But what it allows us to do is make the denominator into a real number, because we know that this 2 minus 3i times 2 plus 3i will give us a real number. So let's just work through this. So on the numerator we have, let me go back to right, we have 5 plus 4i times 2 plus 3i, and in the denominator we have this multiplied by its complex conjugate. Now if I work through the numerator first, well, this will be 5 times 2 plus 5 times 3i plus 4i times 2 plus 4i times 3i, which is 10 plus 15i plus 8i plus 4 times 3, which is 12, times I times I. I times I is minus 1. So we end up with 10 plus 15i plus 8i, which will give me 23i minus 12. So that gives me minus 2 plus 23i. Now let's work through the denominator. So 2 minus I times 2 plus 3i. That gives me 2 squared minus, so I'm using this identity here. So a plus b multiplied by a minus b gives me a squared minus b squared. So I have a squared, which is 2 squared, minus 3i squared. So I get 4 minus 3i squared gives me, well, let's do 3 squared, which is 9. So 9 times I squared, which is minus 1. So this equals 4 minus negative 9, so 4 plus 9, which is 13. So altogether, putting the numerator and denominator together, we've got, in the numerator we had minus 2 plus 23i, and denominator was 13. We can write this as a complex number by dividing each term in the numerator by 13. So we've got the real part and imaginary part. So a is minus 3 over 13 and b is 23 over 13. Now let's go back to the roots of quadratics. If the roots of a quadratic equation are not real, so they're complex, then they must occur as a conjugate pair. And in fact, we saw this in our example here, where we found the roots of this quadratic. We saw that the roots z1 and z2 were actually a complex conjugate pair. So we can use this to find one root if you know the other root, or even to find the original equation. So let's say the roots of a quadratic, let's say they are two complex numbers, alpha and beta. We often use Greek letters such as alpha, beta and gamma when you want to write down the roots of complex valued polynomials. So let's say alpha and beta are the roots. Well, then we know that when we substitute in either alpha or beta for z into this equation, then it satisfies the equation. It does give us 0. We know that z minus alpha must be a factor of the quadratic, and so must z minus beta. And this allows us to reconstruct the quadratic with alpha and beta in it. So if I multiply these two brackets out, I get z squared minus, so I've multiplied z by z, so minus z times beta minus z times alpha plus alpha times beta. So I get z squared minus beta plus alpha times z plus alpha beta equals 0. And so we can see that even if we get given one of these roots, beta, say you get told that beta equals, 7 minus 2i, then you automatically know alpha. Alpha must be the complex conjugate pair. And then you can write down this equation. You can simply write down z squared minus alpha plus beta, so 7 minus 2i plus 7 plus 2i times z plus the multiple of these two, so 7 minus 2i times 7 plus 2i. So here I've just, like we have alpha times beta here, I've just multiplied these two together, and here is alpha plus beta as we have over here. This allows us to reconstruct the quadratic and find what the quadratic equation actually was just from one of the roots. So we know that these two multiplied by each other will give us a real number, because a complex number times by its complex conjugate is real, as we showed before. And these two will give us some real number as well, because the minus 2i and the plus 2i will cancel out. So let's work out what the quadratic actually is in this case. We have z squared minus 7 minus 2i plus 7 plus 2i. So I've got two 7's added together, that gives me 14, And as we said, the minus 2i and plus 2i would cancel out, so 14z plus, let's multiply out these two brackets now, so a squared minus b squared. So we've got 49 minus 2 squared is 4, I squared is minus 1. So 49 minus negative 4, which is like adding 4, so we've got 53. So this is the quadratic, which has roots 7 plus 2i and 7 minus 2i. And you can verify this by going backwards and now using the quadratic formula to work out these roots, but this is how, given just one of the roots, we can find what the quadratic equation was. Now let's look at solving cubic and quartic equations. So we can generalize the rule that we've used so far for quadratic roots to any polynomial with real coefficients. So if we have a polynomial f of z, so some function of z, maybe it's a cubic. If it's a cubic, it looks something like this. And let's say it has real coefficients, so a, b, c, and d are all real numbers, then this cubic we know will have 3 roots. For a cubic equation with real coefficients, either all the 3 roots will be real, or one root will be real, and the other 2 will form a complex conjugate pair. So whenever any polynomial has a complex root, then another root of that polynomial must also be its complex conjugate pair. We can't have a situation where this has 2 real roots and 1 complex. It's not possible. If there is a complex root, it must exist with its conjugate pair. So the only 2 options for the roots are either 3 real roots or 1 real, 2 as a complex conjugate pair. Now let's look at quartics. If we have a quartic function, so quartic is a polynomial with highest degree 4, so the highest power is 4, looks something like this. If we have a quartic equation, this will have 4 roots, so 4 values of z for which this function does equal 0. Either all 4 roots will be real, which is probably the scenario you have seen up till now, all 4 real roots, or there may be 2 real, 2 again as a complex conjugate pair, or there are 4 complex roots where 2 are conjugate pair and the other 2 are a conjugate pair. So just to summarize, if there is a complex root to any polynomial, then it must exist with its conjugate pair. Its conjugate pair is definitely going to be a root of that equation as well. Now let's look at an example of finding the roots of a cubic equation. So I've got this example question. If minus 1 is a root of this cubic, we are asked to find the value of k and also find the other 2 roots. So we know because it's a cubic it will have 3 roots, we've been given 1, which is minus 1, and we want to find the other roots. So let's first start with finding k. So if minus 1 is a root of the equation, I can just substitute that in for z, and I know that this equation will be equal to 0 because it's a root. 3 times minus 1 plus k equals 0. So minus 1 cubed is just minus 1 minus minus 1 squared. Minus 1 squared is 1, so I end up with minus 1 again. Plus, plus minus 3, so minus 3 plus k equals 0, so minus 5 plus k equals 0, so k equals 5. So we figured out what our cubic equation is. It looks like z cubed minus z squared plus 3z plus 5 equals 0. So this is our cubic. Now we want to find the other 2 roots. So we know minus 1 is a root, which tells me that z plus 1 must be a factor. Again, if you're unsure about the factor theorem, I will link it below. So z plus 1 is a factor, so if I divide our cubic by this factor, I will get another factor of this cubic. So let's go ahead and divide these. So z cubed divided by z gives me z squared. So now I write down z cubed plus z squared. If you're unsure on how to divide 2 polynomials, I'll also link this below. So I'm left with minus, remember we're taking these away, so minus 2z squared plus 3z plus 5. Now I'll have minus 2z and we're left with 5z plus 5, which we can easily see will just give us a plus 5 at the end there. So we now know that z squared minus 2z plus 5 is a factor of our cubic. Now we can find our other two roots. So this is now a quadratic that I have to find the roots of. I'm going to use the quadratic formula, so which gives me minus b, which is minus 2, so just 2, b squared, which is 4, minus 4, a is just 1, c is 5, all over 2 times a, which is 1, so just 2 in the denominator, 2 plus or minus 4 minus 4 times 5, so 4 minus 20, which gives me minus 16 over 2. Now the square root of minus 16 will just give me 4i, which is quite nice. So dividing the numerator by 2, I end up with 1 plus or minus 2i. So we can see that the other two roots do form a complex conjugate pair.